In the previous deep reality talk on the computational universe, we learned how the universe continually computes itself and everything in it, including us. This now enables us to understand how particle interactions create what we call space-time. This opens the path to the long-sought unification of quantum theory and relativity in a manner that's scientifically consistent with both theories. The apparent incompatibility of relativity and quantum theory is the most important unsolved problem of modern physics. But there's a single simple insight that reveals how to accomplish this long-sought unification. And not only that, this same simple insight simultaneously resolves the apparent paradoxical nature of the quantum world. The key is to understand that the apparent incompatibility between quantum theory and relativity is due to their very different models of space-time. Both theories view space-time as a preexisting container within which events occur, but the space-time of quantum theory is passive and unchanged by events, whereas the space-time of relativity is dynamic and affected by events. It curves as masses move within it. In these very different views of space-time lies the apparent incompatibility of relativity and quantum theory. So the key to unifying them is a single new model of space-time compatible with both theories. And this becomes easy when we realize what space-time really is. The key is to realize that space-time is not a pre-existing container in which events occur, but a data structure created by events as they occur. Specifically, what we call space-time is created by elementary particle interactions, and I'll explain how this works. But first note that if space-time is created by particle interactions, then it's automatically going to be consistent with quantum theory, and when space-time is simply scaled by the presence of mass energy as it's created, it's automatically consistent with relativity as well. In this way, both theories can be unified. So this clearly looks like the correct approach. And in addition, all the apparent quantum paradoxes disappear, because all the paradoxes of quantum theory, such as non-locality, are with respect to a pre-existing space-time that no longer exists. So when quantum events create space-time, every one of these seemingly paradoxical aspects of quantum theory disappears. So this approach is doubly promising. Also note that even though we imagine we see an encompassing empty space around us, we never actually observe it. All we actually observe is objects with dimensional relationships to each other and to ourselves. Our brains try to tell us there's an empty space between these objects, but that empty space is completely unobservable. So there's no way to confirm it actually exists. Now, in the previous deep reality talk, we found that the quantum vacuum is a formless computational space, and that particles are actually numeric data within this computational space. We can understand this by understanding how virtual reality works. A virtual reality exists only as data in the controller's memory in a completely non-dimensional form. Only in the virtual reality headset is this non-dimensional data displayed dimensionally as the very convincing illusion of a three-dimensional space. In the same way, actual particles and interactions in the real world are data in the computational space of the quantum vacuum, and it takes a brain to act as a headset to display this data dimensionally in its simulation of reality. Only then do we get the illusion we live in a surrounding three-dimensional physical space. Okay, so if particle interactions create a space-time compatible with both relativity and quantum reality, how does this work? First, all particle interactions exactly conserve total mass energy. The total mass plus energy of all the particles entering any particle interaction is exactly equal to the total mass energy of all particles coming out of the interaction. This is always true, whether particles change into other particles or just scatter off each other. the total mass energy coming out always equals the total mass energy that came in. Now this conservation of mass energy produces dimensional relationships among the numeric positions and velocities of the particles exiting an interaction, because their velocities are part of the total energy conserved. These dimensional relationships are an example of entanglement. Entanglement is a universal principle that holds at all scales and is easy to understand with a simple example. For example, if a raisin chocolate chip cookie is broken into two parts, the two parts will become entangled on their ingredients because the total amount of all ingredients is conserved. If we know the number of chocolate chips and raisins in one half, we automatically know the number in the other half because they must equal the number in the original cookie. So the numbers in each half are related to the numbers in the other. Thus we can say that the cookie breaking interaction causes the two resulting halves to become entangled on their raisins and chocolate chips. So when mass energy is conserved in particle interactions, the resulting particles become entangled on their mass energies. The resulting masses and energy of all emitted particles will have dimensional relationships to each other because their total must equal that entering the interaction that produced them. So every particle interaction generates dimensional relationships among its resulting particles. And since all particles in the universe are part of a single universal interaction network dating back to the Big Bang, there will be dimensional relationships among all the particles in the universe. And because all the objects in the universe are composed of particles, all objects in the universe become dimensionally interrelated. Now the key to understanding the true nature of spacetime is to understand that this universal network of dimensional relationships among all particulate objects is what our brains simulate as an encompassing physical spacetime. All the objects in the universe actually consist entirely of data, including the data of the dimensional relationships. Our brain samples this data by interacting with it, thereby establishing our dimensional relationships with external objects. And then our brain projects all this data into the semblance of a three-dimensional space around us within which it arranges the objects. If we have a set of numbers representing the location of objects, the easiest way to make overall sense of it is to place the data in a three-dimensional graph. This is exactly what our brains do. They take the data of the individual dimensional relationships of objects and construct an internal three-dimensional graph called empty space and place all the objects within this graph. That enables us to make instant sense of the dimensional interrelationships of everything around us all at once, even though it's actually all an illusion. All observers, including ourselves, are part of this universal network of dimensional relationships, because every observation boils down to particle interactions between the observer and things observed that establish dimensional relationships among them. When we observe an object, we are establishing a dimensional relationship between it and us. Thus our brains take the numeric data of the universe, sampled in our neurons, and display it in our heads as a surrounding three-dimensional space that makes it easier for us to make sense of the world around us. It's an enormously useful evolutionary adaptation, but it's completely illusory because the actual universe consists entirely of logical relationships among numbers in the computational space of the quantum vacuum. So what our brain displays as a surrounding physical space is actually its internal graph of numeric dimensional relationships among objects. Space-time is actually a data structure in our brain's simulation of reality that our brain tells us is a physical structure in the external world. Okay, this is how the space-time we think we see around us is computed by particle interactions. And it automatically incorporates relativity because the dimensional relationships among particles are scaled by the amount of mass energy present as they're computed. This scaling automatically produces the correct curvature of space-time by masses, or in the improved deep reality model, the resulting intrinsic spatial velocity densification. But we still need to incorporate quantum space-time into the same model to unify it with relativity. How does this work? To add quantum reality, we just need to show how the fuzzy dimensionality of the quantum scale is computed by particle interactions at the same time it computes relativistic spacetime. Now, there's a very simple way to do this based on the processor model from the previous deep reality talk on the computational universe. Recall from that talk that the universal processor computes relativistic space and time velocities simply by allocating a fixed number of processor cycles to compute every separate coherent process. First, the velocity in space is computed, and then any leftover cycles are used to compute velocity in time. In this way, the total space plus time velocity of everything in the universe is always computed equal to the speed of light. The source of the speed of light is the fixed number of processor cycles used to compute every process in the universe. This is how the key fundamental principle of relativity works. So to incorporate quantum indeterminacy, we just have the same universal processor randomly oscillate between space and time velocities at the quantum scale as it computes the universe. This simple addition to the universal processor model is sufficient to account for quantum indeterminacy and have the processor compute a space-time that's compatible with both relativity and quantum theory, which is exactly what's needed to unify them. Thus, we have a simple model of a universal processor that simultaneously computes a unified quantum and relativistic space-time. We have a working model of quantum gravity. All right, so how do the random particle scale processor oscillations account for quantum indeterminacy? The two key examples of quantum indeterminacy are the Heisenberg uncertainty principle and wave functions. The processor oscillations automatically explain both. Take the uncertainty principle, which states that it's impossible to exactly measure the complementary variables of either energy and time or position and momentum, that is velocity, at the same time. This is clearly telling us there's an intrinsic limit to how accurately time variables and space variables can be simultaneously measured, which implies a random oscillation in how they're actually computed. This is exactly what we would expect if the velocities of time and space were always being randomly conflated at the quantum scale as they're being computed. It's as if we're trying to measure the time and space velocities of some particle by placing it on a graph where the space and time axes of the graph are constantly oscillating at the particle scale. If the reference graph itself is constantly oscillating at the particle scale, it becomes impossible to get an accurate reading of how the particle is behaving in both space and time simultaneously. We can get an exact value of either at a single point in time, but the value of the other will be uncertain at the scale of the oscillations. So just introducing random quantum scale oscillations between space and time velocity as they are computed automatically gives us the uncertainty principle. Now, the other major example of quantum indeterminacy is wave functions. Current interpretations of quantum theory think of particles as wave functions in a pre-existing space, and these wave functions are interpreted as the particles being smeared out in this space with some probability of being anywhere within its wave function. But since there is no longer any pre-existing space, this interpretation of wave functions can be correct. The correct model is that the movement of particles is computed in computational space as simple data values, and it's only when these movements are dimensionalized in comparison to other particles that they look like wave functions. This is demonstrated by the fact that the entire wave function itself has an exact spatial velocity and time evolution that reflects the computational movement of the underlying numeric particle. It's only the dimensionality within the wave function that's indeterminate. The wave function itself has an exact trajectory. Now, wave functions do provide very accurate mathematical descriptions of quantum particles and are still valid, but their meaning is now reversed. Instead of describing particles smeared out in a pre-existing physical space, they actually describe how space may be dimensionalized as particle interactions create it. The equations are exactly the same, but the interpretation is turned on its head. In this manner, deep reality remains consistent with the equations of quantum theory. Now, each particle interaction and the dimensionalities of the particles resulting from it are computed as a coherent process by a new application of the universal processor with its own unique random oscillation pattern. A coherent process is one computed by a single processor app with a single oscillation pattern. Because they are computed by separate random oscillation patterns, the dimensionalities of each coherent process will be indeterminate with respect to all others at the quantum scale of the oscillations. This means that the dimensionalities of particles look like wave functions from the perspective of other particulate structures, such as an observer or a measuring instrument, because wave functions accurately describe the oscillation patterns of their dimensionality as it's computed. So the simple fact that each set of coherent particles produced by an interaction is computed by a separate oscillation pattern makes their dimensionalities indeterminate with respect to those of all others at the quantum scale. This is the computational source of wave functions, which are now properly reinterpreted as the probabilities of how quantum space-time can be dimensionalized when particles interact. Okay, now there's just one more piece to complete the picture. When particles interact, they must have exact dimensional relationships to each other for their mass energies to be conserved. This means that their dimensional indeterminacy must be resolved to exact values for an interaction to take place. This occurs through a process called decoherence, which randomly selects mutually exact dimensional relationships from the two particle wave functions as they interact. This produces the exact mutual dimensionality necessary for mass energy to be conserved in an interaction. Only through decoherence can mass energy be exactly conserved so that particles can interact. Now, decoherence occurs because a particle interaction is computed by a new processor application with a new oscillation pattern that now applies to both interacting particles. The whole interaction, including the resulting particles, is now computed as a new single coherent process with a new unique random oscillation pattern. So decoherence is a handoff from separate applications computing separate particles to a single new application computing their interaction and results. Two separate oscillation patterns are replaced by a single new oscillation pattern that resolves the dimensional indeterminacy to conserve mass energy. This dimensional indeterminacy is resolved when the new application begins computing the interacting particles as a single new coherent process with its own new oscillation pattern. So the interaction of two particles randomly resolves their dimensional indeterminacy with respect to each other to exact values. This is what used to be called wave function collapse before decoherence was discovered. So we now have an overall model of the universal network of dimensional relationships produced by particle interactions that's consistent with both quantum reality and relativity. The entanglement network of all particles in the universe consists of exact dimensional values with respect to each other, connected by fuzzy lines representing the relatively indeterminate dimensionalities of individual particles between interactions. Some particle interactions occur rapidly, but many persist through time. All the particles bound in atoms and molecules that make up most of the universe are interactions that persist through time in the entanglement network. The dimensional relationships of bound particles are a major contributor to the overall data structure of space-time. Now, the entire entanglement network of all particle interactions throughout the history of the universe extends conceptually back to the Big Bang, but only the current present moment slice is the actual current universe. The current data state of all the current particles in the universe is the data that makes up the entire universe. This data makes up the entire observable universe, and this data is the observable universe. The entire observable universe consists of all the data of all actualized particles, and that's it. There's nothing else to it. This data includes the dimensional interrelationships among all particles encoded in their individual numeric particle values. Thus, the current data of all the current particles in the universe contains both the structural and dimensional data of the entire universe. It's the actual data state of the entire observable universe that encodes both all particle structures and their dimensional interrelationships. This is what our brains sample and interpret as physical objects in a physical space-time, but in reality it's all just particle data. Now, the mutual dimensionalities of particles in interaction nodes are exact. This means that the overall dimensionality of the entire node network is exact at the classical level of human observation and at the level of relativity. However, the fuzzy particle lines coming out of every particle interaction take the form of wave functions in their dimensionalities because each is being computed by a different random processor oscillation that conflates their spatial and temporal velocities differently. Thus, the entire entanglement network of the universe consists of exact interaction nodes connected by wavy lines in the form of particle wave functions. As wave functions decohere in new interaction nodes, their dimensionalities exactly align with each other because their interaction is now being computed by a single new processor application with its own new oscillation pattern. So the totality of all exact node interrelationships accounts for the exact dimensionality of relativity, while the fuzzy behavior of particles between interaction nodes explains the dimensional indeterminacy of the quantum world. This is how the dimensional space-time that's constructed by particle interactions accurately explains quantum indeterminacy at the particle scale while becoming exact at the relativistic scale. And this is exactly what we observe in the world around us. Recall that the source of the apparent incompatibility of quantum theory and relativity was due to their different models of preexisting physical spacetime. So by replacing both these physical preexisting spacetimes with one computed in a manner consistent with both relativity and quantum theory, we automatically achieve the long-sought unification of relativity and quantum theory. In essence, the universe consists of myriads of quasi-independent dimensional fragments at the quantum level that are stitched together by successive particle events to create a consistent overall space-time at the classical relativistic level. Then in turn, new particle interactions create additional fuzzy dimensional fragments waiting to be stitched together by subsequent decoherence events. And so the process continues forever, dynamically creating relativistic spacetime at the classical level out of fuzzy dimensional fragments at the quantum level. Now, as promised, this model also resolves the apparent paradoxical nature of the quantum world. Take the standard spin entanglement paradox. A particle interaction creates two particles that have entangled equal and opposite spins, and they fly off in different directions. The spins of the particles are created as a new dimensional fragment that's inherently indeterminate with respect to a laboratory spin detector. So a measurement of one particle spin can find it in any random orientation. But thereafter, a measurement of the spin of the other will always find it in the exact opposite orientation. This is now simply explained. The particle interaction that created the equal and opposite spins was computed as a coherent process by a single processor app with a single random oscillation pattern. The spins were exactly computed as equal and opposite within this dimensional fragment, so spin would be conserved. Thus, the two mutually opposite spins were computed as a completely independent dimensional fragment, one of myriads that gets stitched together to form a consistent space-time at the classical scale. Thus, the spins were always exactly equal and opposite within their dimensional fragment as the particles moved away from the event. However, this exact spin relationship was indeterminate with respect to a spin detector not being computed with the same oscillation pattern. Now, the measurement of the first spin was a decoherence that randomly aligned the entire dimensional fragment of both spins with the detector. Since both spins were part of the same dimensional fragment, the alignment of one with the detector automatically aligned the dimensionality of both with the detector. So when the second spin was measured, it was automatically found to be equal and opposite because its spin dimensionality had already been aligned with that of the detector. So there was never any faster than light transmission from one particle to the other, telling it how to align itself. It was just a matter of a single dimensional fragment encoding the opposite spins being aligned with the detector as one of the spins was measured. The measurement of one spin automatically stitched the whole dimensional spin fragment into the already existing space-time of the laboratory and detector. And as to the problem of non-locality, in a computational universe without a pre-existing physical space-time, everything is automatically non-local. So non-locality is no longer paradoxical, it's normal. This demonstrates how particle interactions creating space-time automatically resolves the apparent paradoxical nature of the quantum world. Other examples are given in my books. Now, this talk is a simplified overview of the entire theory. Refer to my books on universal reality, especially Universal Reality 2.0 for the complete details. The unification of quantum theory and relativity is an enormously important breakthrough that emerges naturally from the deep reality computational universe. And in turn, deep reality has all sorts of profound new implications for time, cosmology, and even the nature of existence and consciousness. These will all be explored in upcoming deep reality talks. Stay tuned and subscribe to be notified.